This month, the sky at night is all about measuring the sky at night. We're getting to grips with our home galaxy, the Milky Way. Maggie looks at how, over the ages, technology has driven astrometry, the science of measuring the heavens.
John Flamsteed was the Astronomer Royal. In the 17th century, he was able to calculate the positions of 3,000 stars.
Chris discovers what we now know about how the galaxy formed, thanks to the very latest technology.
We were able to build a family tree of the Milky Way.
We'll discover how the latest data from the Gaia mission solved a 300-year-old problem.
The Gaia data turned out to be so good that it's actually been detected already, so it's ahead of schedule.
And I get to see how we really can predict the future using the stars. As time goes on, you can see that his belt goes a bit wonky and he loses his sword altogether.
Welcome to the sky at night. Since people first looked up at the sky, they've made patterns out what they saw, and then made maps. Maggie has been to the Royal Astronomical Society to trace the long history of our measurement of the stars.
Virtually all civilizations across the globe took an interest in the night sky. And many, from the Chinese to the Egyptians, from the Babylonians to the Greeks, made maps of the stars. A pretty impressive feat, considering their only means of observing was the naked eye. The Royal Astronomical Society has a wonderful collection of books and papers. They show how our progress in accurately measuring and understanding the stars has gone hand in hand with technological advances. They're looked after by curator Sian Prosser. She explained to me how even in the 15th century, astronomers were still using records made in the 1st century by Ptolemy. These were improved by Islamic scholars like 𝐿𝐢 Beg, who used sextants and quadrants to improve accuracy, and by European observers like Tycho Brahe, whose work was further enhanced by Johann Kepler's mathematics. But in the 17th century, the arrival of the telescope changed everything. So, Sian, we've moved on, and this in very faint writing says Flamsteed's Atlas. It looks well loved. So what have we got here?
John Flamsteed was the Astronomer Royal. In the 17th century, the age of the telescope. He was able to calculate the positions of 3,000 stars.
That's impressive. See, going from Ptolemy's 1,088 to now 3,000 stars.
The sky's really opening up. And after Flamsteed's death, this atlas, known as the Atlas Coelestis, was published, which shows the positions of the stars in a series of beautifully engraved plates, where you have the mythological figures of the constellations and the grid lines showing the right ascension and the declination, a bit like the latitude and the longitude.
This almost feels like sort of a sacred text to me, but someone's written in the margins.
It's a very well-used book. This atlas belonged to Caroline Herschel and her brother, William Herschel. William Herschel was one of the great astronomers of the 18th, 19th century, well known for discovering the planet Uranus in 1781. They would use this book as a reference to accompany their nightly observations. And because of the greater resolving power of William Herschel's telescopes, which were like 7 foot, 9 foot, then the 20-foot telescope, the 40-foot telescope, they were able to see that what might have seemed like a single star to Flamsteed and his fellow observers was actually a double star or a triple star. So that's why the word double is often written in pencil in the margin.
Yes, I can see lots of them. So they're effectively updating the information.
They're updating the information, though. They're building on the work of past astronomers. And Caroline Herschel was able to publish an updated catalogue of stars based on John Flamsteed's catalogue. She was the first woman to be awarded the gold medal of the Royal Astronomical Society in 1828.
That's amazing. But I just love the idea that Caroline and William were sort of poring over this, and now we are too.
Yeah, they
it's
were.
Sort of that link with history. So I guess with this atlas, we're reaching the peak of what could be done with looking through a telescope. So what was the next evolution?
The next evolution comes in the 19th century with the advent of photography. So what I have here are a few examples of some negative photographic prints. Each plate has a grey background and a grid and literally hundreds of black dots of varying size. And this is basically the representation of the sky as photographed in this case by Royal Observatory Greenwich.
So I suppose to map stars, you need telescopes across the world. And with photographic plates, you could store that information and compare that information and truly make a glorious star catalogue.
Yeah, so you'd have an objective record of what was seen in the sky exposed on the photographic plates.
Yes. Yeah, no interpretation needed. And we're able to investigate in much more detail and compare and contrast, I guess, with other photographs.
Yes.
Each time improvements in technology expanded our understanding of the heavens, we ended up with new questions. Over time, even things that once seemed certain, like the fact the stars were fixed in the sky, were challenged. I'm at the Institute of Astronomy in the University of Cambridge in the dome of my favourite telescope, the Northumberland, which was given to the university in the year 1833. That same year, down the road at Greenwich, Astronomer Royal John Pond was finishing his catalogue of 1,112 stars, his map of the night sky. In the catalogue, there's a remarkable note where he says that if you could measure accurately the motions of all the stars, you'd be able to deduce the motion of the sun through the galaxy. But he also says that because the stars are moving on their own orbits, the whole thing is almost certainly hopeless. And he concludes that it may have to become a subject of interest for future ages.
4, 3, 2, 1, top, décollage.
That future age has arrived. In 2013, the European Space Agency put a satellite into orbit that will solve all of John Pond's problems. Its mission is to produce an accurate, three-dimensional, dynamic map of the Milky Way by measuring the positions and movements of 1 billion stars. At the end of 2020, the Gaia team released their third set of results. I've come to see Jerry Gilmore to find out what this spectacular star map tells us.
This is a 1:10 scale model of the Gaia spacecraft. So the real thing's half the size of a tennis court, but this is the model. This sun shield folds up for launch because you can't launch something that's this big,
right,
and then unfolds in space. So the sun is underneath, and Gaia itself is sitting in the cold and the dark to keep it stable. This ring on which everything hangs together is the most stable silicon carbide structure ever built. Gaia has two mirrors. So there's one aperture where the starlight comes in here and goes across to this telescope, and light comes in here and goes across to this telescope, and then down to this here, which is the heart of Gaia. It's the camera. Largest camera ever built and put into space. It's over 1 meter long. It's 1 billion pixels. So as Gaia rotates about once every 8 hours, these two telescopes scan a path completely around the sky, and so we get a stripe around the sky every 8 hours. And so we've got a movie. Basically, it's a high-definition movie, but all this is handled by this amazing team of 500 people who turn this high-definition movie into fundamental science.
How does it work?
It works the same way our eyes do. Our eyes measure distance from the slight difference in angle from one eye to another, and so that's fundamentally what it does. So Gaia takes an image on one side of the sun in the spring, another one in the autumn, crudely, and compares the two of them. But the position accuracy is such that, well, like all numbers in astronomy, they're ridiculous. But so to use an analogy, it's the individual position of the star is known to an accuracy equivalent to the thickness of a fingernail, measured by us here, where the fingernail is in Sydney.
Blimey. Why do we need that level of precision?
Well, the answer is really simple. It's because space is big, actually. Space is really big, and that means stars are very far away. And you need that precision to see the parallax of a star because stars are so far away.
And then that precision lets you do wonderful things. One thing that I think is particularly fun is this determination of the sun's orbit around the galaxy. Tell us about that.
Okay, so one of the the precision measurements that you can get, of course, is that Gaia, as well as seeing all the stars, sees an awful lot of quasars, and so they're so far away they don't have any parallax, they don't have any.
So these are very
motion.
distant galaxies.
They're very, very distant galaxies, halfway back to the Big Bang, and they don't move. They don't appear to move because they're so far away. And so because Gaia is actually moving with the sun as we go around the Milky Way, by comparing the apparent position of the centre of the solar system to those quasars, you can already see this acceleration. Of course, we knew we were going to be able to do it. It was part one of the, in the original proposal for Gaia, it said, hey, we're going to be able to do this, but it was thought we would be doing it in maybe 5 years' time after much, much more data. The Gaia data turned out to be so good that it's actually been detected already, so it's ahead of schedule. But after 300 years, you know, we've done it.
Nice to tick that one off and move on.
Exactly, yes.
Gaia is one of the most technologically advanced instruments ever put into space. Its high-tech, rock-solid frame and billion-pixel camera reveal our galaxy in exquisite detail. And yet Jerry is already dreaming of future missions.
The other thing you want to do is go to even higher precision. And then you'll see not just in our immediate Milky Way neighbourhood, you'll see all the other galaxies near us moving as well. And that's a fundamental test of Big Bang cosmology. You can actually trace the orbits of the individual galaxies right back to the Big Bang and say, what was it like way back then? And so that fundamental cosmology is another exciting topic waiting for Daughter of Gaia.
Right, well, for now, we'll enjoy the Milky Way. Jerry, thank you so much, and we'll talk to you again soon.
In the early days of stellar map making, the method was simple. Look up and draw what you see. But these days, it's a lot more complicated. The electronic eyes we use to gather data reveal far more than we can see with our real eyes. Chris has been talking to one researcher who has used AI to interpret Gaia data on globular clusters and shed light on the Milky Way's turbulent history.
Globular clusters are large groups of stars that are orbiting the Milky Way. They're compact, they're only a few light years across, and they have hundreds of thousands to 1 million of stars. And they're very old. They're almost as old as the universe itself. And for that reason, they can tell us a lot, because we think galaxies like the Milky Way formed through the merging of smaller galaxies. And we have reason to believe that many of the globular clusters that are now orbiting the Milky Way actually formed in smaller galaxies, didn't form in the Milky Way itself, but formed in those smaller ones. So we can basically use globular clusters to figure out what the building blocks of the Milky Way were like.
If you think about the history of the Milky Way, it was this island universe that sat on its own. Why do we have this idea of mergers?
We actually see it happening in the universe today, but also when we look further away and we look back in time, we see it happening. We see galaxies merging with each other. Also, in our current models for the universe and how we simulate a galaxy formation on big computers, we see this happening all the time.
Well, I'm glad you mentioned simulations, because that's the key to this piece of work that you've been leading, right? This comparison between what we see and what the computers tell us.
Yes, by taking those simulations and learning from them what that relation is between globular clusters and the galaxy building blocks within which they formed, and applying that to the globular clusters of the Milky Way, we've been able to piece together how our own galaxy formed.
Let's have a look at the simulation.
What you see here is a cosmological simulation of a Milky Way mass galaxy, a Milky Way-like galaxy. And in gray is shown the gas, which in the early universe is fragmenting into all of these small seeds where galaxies start forming. Those colored dots are the globular clusters in the simulation.
So your computer knows where they are and how they're moving.
In the simulation, we can relate the properties of, say, the globular clusters that came in with this galaxy that you see.
Yep, there we go.
We can take the properties of those globular clusters and relate them to the properties that that galaxy had. And it turns out that that gives us very strong relations between, for instance, the chemical composition of globular clusters and the mass of the galaxy that they came from, that we can then go to the real universe and say, well, we've got this group of globular clusters here. what was the mass of the galaxy that that group came from, but also when they merged with the Milky Way. So in a way, we were able to build like a family tree of the Milky Way, where we were able to connect all of those merger events to this tree trunk that is in the Milky Way today.
This family tree for the Milky Way shows it growing from top to bottom. Along the way, mergers with other galaxies occur. Several of these were known about and tied in with known globular clusters. But Diederik and his team thought there must have been more mergers.
And then with Gaia, there was this mysterious group of globular clusters found. And we were like, well, that is exactly the number of globular clusters that we expected. They're roughly having the orbits that we expected. And we had predicted that there was this galaxy because it was mysterious. We called it Kraken. We had predicted it must have existed, but we didn't know. And now we ran our new machine learning techniques on that group of globular clusters. And yes, it was exactly a galaxy with the properties that we expected, that we called Kraken. And it merged with the Milky Way about 11 billion years ago. We think that this is actually the most major merger, so the biggest, most transformative merger that the Milky Way ever experienced. And now, thanks to Gaia, we found the globular clusters. Thanks to our simulations, we were able to figure out what its properties were. And I think this is really a fantastic example of how different fields in science can come together and figure this out.
Yeah, and how amazing that we didn't know about the major event in the Milky Way's history until recently.
It's 11 billion years
rather
ago.
Fun. Yeah.
Thanks to Gaia and the Milky Way and those simulations put together, we think we can start to do this for other galaxies too, where we have less information.
Well, I will look forward to those results. Thank you for telling us about your research, and we'll talk soon.
Thank you.
If you look at the Milky Way today, you might think that catastrophic collisions are a thing of the past. But you'd be wrong. Wyn Evans has his eye on mergers that are being revealed by Gaia and happening right now.
We now know that in the remote past, there was this encounter with a very large, primitive galaxy, sometimes called the Sausage Galaxy or Kraken or whatever. Now we can see the Sagittarius Galaxy merging with the Milky Way, and in the future, in 2 billion years' time, we know that the Large Magellanic Cloud will merge with the Milky Way.
So Gaia has provided us with evidence for these many mergers in the distant past, but this is a process that's still happening, for example, with the Sagittarius dwarf. Tell us about that galaxy.
Well, the Sagittarius is a puny thing now. It's really been beaten up by the galactic tides. In stellar mass, it's about 10 million solar masses, and it's the other side of the galaxy behind the galactic bulge, about 24 kiloparsecs away from us. And so this little thing has enormous tails, and we can see these clearly in the Gaia data. So there's a leading tail that arches up from behind the bulge, up over our heads and out to about 40 kiloparsecs. And that sounds big enough, but the trailing tail is even bigger. That comes off the bottom of the Sagittarius, underneath Earth, and it goes out to about 100 kiloparsecs. And this has been traced back to the effects of the Large Magellanic Cloud. So that's the next big galaxy that's coming in after Sagittarius. And so in the remote past, the Sagittarius and the Large Magellanic Cloud were close enough so that the stars in the leading tail of the Sagittarius were perturbed, and we see the effects of that perturbation today in the motions of stars in the leading Sagittarius stream. It's quite remarkable.
The Gaia data has allowed the modelling of this snail-slow three-way car crash. Sped up, you can see how the orbiting Sagittarius galaxy is being destroyed, producing long trails of stars, which are in turn affected by the presence of the incoming Large Magellanic Cloud, shown here in green. It's amazing to think we can sit here and talk about something that happened so long ago with precision. So thank you very much for talking to us, and we'll come back after the next data release.
Please do. I think the next data release will be even more exciting, because for the first time, we will be having spectroscopy from Gaia. There will be lots of spectra released for the very first time. Previously, we've just had astrometric solutions and radial velocities. So there are more treasures to come from the Gaia satellite.
The Romans called the band of stars that run across the night sky Via Lactae, Milk Road. They, and the Greeks before them, thought that it was due to a divine accident involving breastfeeding. Anyway, we now know that what it actually is a side view of our galaxy. Here's Pete to tell you where to find it.
It's been a fantastic day today. The sun has been shining all day, and that has followed through into the night time because we've now got a beautifully clear sky and I can see the stars of spring shining away up there. But one thing which is very evidently not there at the moment, even from my relatively dark sky location here, is the Milky Way. And there's a reason for that. It's due to the fact that the Milky Way is basically a disk of stars, and the sun sits about 2/3 of the way out from the center of that disk towards the edge. Now, in the spring and autumn months, the arrangement is such that we're looking out, when we look up at our night sky, at right angles to the plane of the galaxy. So we're looking through a very thin layer of the Milky Way, and we don't really see the misty band of stars up there. In the winter, we're looking out in a direction opposite to the core. And that means that the view of the Milky Way we get is pretty weak. In fact, it runs down to the east of Orion, and unless you knew it was there, you'd probably miss it altogether. But it's the summer months where the Milky Way really shines at its best, because then we're looking towards the core, and that's the brightest part of the Milky Way. Now, at the moment in the spring, you can still see it. But what you have to do is get yourself to a really dark sky location, the darker the better, and you have to wait up until the early hours of the morning, and then you'll see the band of the Milky Way rising in the eastern part of the sky. It's a pretty spectacular sight if you have opportunity to go and see it. Now, if the moon is up, its glare will wipe out the Milky Way. But there is something interesting happening with the moon as we go through into next month, because on the 10th of June, we will have a partial solar eclipse visible from the UK. The eclipse from the centre of the UK starts at around 7 minutes past 10 in the morning. That's British summertime. Now, you have to be really careful, of course, looking at the sun, because you will damage your eyesight or you will damage equipment if you don't do it properly. But in order to show you how to do that, I'm going to have to wait for the sun to come up. There are various ways you can enjoy the eclipse of the sun safely. You might have a pair of eclipse glasses or get hold of a pair of eclipse glasses. As long as they're certified, you just put those on and you can look directly at the sun through them. And that's a very safe way to view what's going on. Another low-tech method is to use a piece of paper with a hole in it. Here's what I did earlier. There's a hole. Hole needs to be about 1 millimetre, 2 millimetres across, and then use a piece of white card as a screen. And where the sun's light comes through the hole, it creates a tiny image of the sun, and that will allow you to watch the progression of the eclipse quite safely. Now, if you have a telescope, there are other ways to filter that. If you're lucky enough to have a hydrogen alpha filter, which fits over the front of the telescope, you can view the sun in H alpha and watch the eclipse as it progresses quite safely that way. An alternative method, which is a bit cheaper if you haven't got an H alpha filter, is to use what's known as a white light solar filter. So a white light solar filter you typically buy in A4 sheets, and then you have to make your own. You make a roll of card, and then that slips right over the front of the telescope like so it doesn't blow off in the wind. It's nice and secure. However you choose to view the partial eclipse, do it safely and enjoy the event.
The Milky Way you can see tonight will look identical to that viewed by your distant ancestors. But if Gaia has one message for us, it's that our sky and our galaxy are far from static. Maggie is looking to the future.
For most of human history, there's been no concept of a dynamic universe. In fact, most people thought that the stars stay at fixed positions. And that seems to be reasonable because they don't seem to move relative to each other. But now we've seen the motion of the stars, it means that we can wind the clock back and look into the past, or even wind the clock forward. So it's actually true. The future really is written in the stars. This video shows the movement of stars over the next 1.6 million years. Each of these lines tracks the position of the star. It's a far cry from the fixed canopy that our ancestors thought determined our fate. And if we look at some of the constellations that we take as a fixed feature from here on Earth, then you can really see the dynamic galaxy at work. Take this time-lapse video of Orion in the future. As time goes on, you can see that Betelgeuse on his top left-hand corner wanders off the screen altogether. His belt goes a bit wonky, and he loses his sword altogether. The Gaia data has provided us with a staggeringly beautiful and accurate three-dimensional picture of our galaxy. Something that those early pioneers of astrometry would have never imagined. But perhaps best of all, everybody can have a copy of this map. All you need to do is download the app, and then the galaxy is at your fingertips. We really are a privileged generation. Not only do we understand in principle how our universe works, we also have star maps that we can use as time machines. We are piecing together our galactic family tree, and we have seen into the future. So now, we're not limited just to look at the sky at night. We can virtually travel through it, from one end of the galaxy to the other. And this is all thanks to our latest high-tech endeavours at mapping the Milky Way.
That's all for this month. Next month, we're celebrating British space engineering. I do hope you can join us. Until then, good night.
Columbia, this is Houston, reading you loud and clear, over.
Yeah, reading you loud and clear. How's it going?
Roger, the EVA is progressing beautifully.
How is the quality of the TV?
Oh, it's beautiful, Mike, it really is.
Oh, geez, that's great.
I certainly did not have the best seat of the three on Apollo 11, but I can say in all honesty, I was thrilled with the seat that I did have. I knew that I had somehow lucked into being 1/3 of the team that was going to do this wonderful thing, and my function suited me fine. I was very proud of the job that the three of us did getting us to and from the moon. But more than the three of us, there were almost 400,000 Americans working on Project Apollo. And I thank them. They're the ones who don't get recognized. I mean, yeah, sure, I would have preferred to walk on the moon, but that really seemed trivial distinction at the time.
I guess you're about the only person around that doesn't have TV coverage of the scene.
That's all right, I don't mind a bit. Is the lighting halfway decent?
Yes, indeed. They've got the flag up now, and you can see the stars and stripes.
Beautiful, just beautiful.